Kevin Kochek. I'm the founder CEO of Chemical Q Device, here to talk about QML and neuroimaging. In specific, this is with multimodal, so you figure like electronic health records, imaging, cerebral spinal fluid, and basically pulling these things together on the path to greater healthcare QML advantage. So as you can see, so this is the rubric. I'm going to go over some QML first. So this is classification, QC-ware, Roche exponential processing. And then the meat and potatoes of all this is the multimodal. So it's called early fusion, joint fusion, or late fusion. And then the push with all this is basically to get FDA approval, clinical use. Alzheimer's disease across the board is the #1 for prediction, for diagnosis. You also see tau accumulation. This is a big paper by Berkeley and Cambridge as well. Now, last week I went over this is technology growth potential and an ask. So this is basically the intersection of quantum and medical. And in specific, we're talking about medical imaging for most of these things. So this deck and the presentation is available as well. So this first paper is QC-ware and Roche. And basically what it is quantum methods for neural networks and applications to medical image classification. Now that was this month. I think this paper is the type that just keeps getting updated. It's archived. But nonetheless, the two new things with it are basically you have the quantum computer for inner product estimation. For those that are in medical, I'll get to the medical too as well. And these quantum pyramidal circuits, basically these are kind of new discoveries in quantum. And they're basically saying data sets and hypotheses are classical, so these are hybrid approaches. And then you also have learning phases assisted by the quantum computer. So, okay. I should be able to suspend. Okay. So as you can see, QC-ware here and Roche is basically, there's a lot at stake. In medical imaging, 90% of all healthcare data is basically medical imaging here too. So on this particular paper, 16 qubits, IBM Q, the main sources of noise being the device, finite sampling noise. Now they say in some cases, and they do this with classical too, is that noise can help to escape local minimum. The figure in general, you don't want noise around. So they use this retina MNIST. So this is I, and I'll show you the results in the next slide here too. So basically 8-dimensional wound up better than 4. Larger input feature set is more efficient for a harder task. Runtimes need further optimized within quantum cloud. And the future is with better algorithms and heuristics to train better and faster models. So here's the results. Now they did pneumonia, which aren't quite as conclusive, but with retina. So the one on the left was a quantum assisted neural network. So you see kind of like that separation of yellow, orange, and red, or burgundy. And so basically, if you look below, the classical training, classical prediction is still doing quite well. This is another case where it's just, now that we have dynamic circuits and this potential NSF practical quantum computer getting better next year, is that hopefully we'll start to see the separation a little bit more. And like what's on the right, orthogonal neural networks. So you see the yellow and the green. So some aspects incorporating quantum were found to work okay. So this next paper is basically, so this is basically, you have quantum circuits that need to get run on quantum hardware, quantum simulator, and then in specific with this, you have sequential and parallel. So these are these are what gets run. So on the left are sequential linear, sequential exponential. On the right, parallel linear, parallel exponential. And then, so here's basically the advantage. So you're looking at the teals. So the second row is parallel exponential, and then the third row is sequential exponential. And those allow for four Fourier frequencies, so that's preferred. Now, getting into all the medical stuff. So, as you may know, machine learning, and this goes back to even before 2020, is making a huge impact in healthcare. So, not only just looking, so if you just want to look at, say, genomics, and using machine learning in that, and now we're looking at multimodal between, say, genomics, EHR data, imaging data, and the like. So I kind of alluded to this a little bit before. So you have early fusion, multiple data sources converted to same info space, most common. Intermediate, so you have joint stepwise set of models with greatest latitude. And then you have late fusion, so decision level, which is the least common. Now, this is a very important diagram here. So this basically pulls in everything from medical imaging, demographics, clinical notes, time series, genomics, and then, you're either, the fusion is the, multimodal part of this. So you have early, which is most of these, intermediate, and then late. And then you have decision and prediction, which is an algorithm. So you have clustering regression. So in medical imaging, you have classifications such as Alzheimer's positive or Alzheimer's negative. And then this is basically cyclical. So in health centers, you have the data, it goes back to information commons, and then all these things. So you have proteomics, genomics, any that those types of like biomolecules, the studies of those. And especially 90% of the data, depends on the study, but as a whole is imaging. So a lot of these things, the clinical notes, the tests for the patients, especially like for Alzheimer's disease, you have to figure out cognitively where they're at, and that's not necessarily a high-tech thing. It's more like I believe it's called an MMSE. And then this goes down to information transformation, modeling, merging, and then back up to precision health outcomes. And each of these boxes are huge. So we talk about drug discovery and machine learning, diagnosis, prognosis with imaging, target ID, phenotyping, subgrouping. So you have, a mix of everything. All of this information is coming together. Now, this is an interesting graphic because when I start on the left with numbers with neurology, it says 50. And then, so basically out of those, Alzheimer's is the biggest out of all of these that was under study for this review. So it's a pretty good reflection of what's going on as well. But it's just important to note that it's a huge thing. We care about our elderly. It's there's correlations between basically imaging and cerebral spinal fluid and blood tests, and basically pulling these all together. So there are some limitations with data modeling and translation. So for instance, in model testing, lack of comparison with single modality. You have translational support, model building, model training. So there's many things, and especially as these multimodal approaches get a lot more complex, is that it gets a significant more amount of time and resources to make sure you're getting the results that you want. So of the 128 papers that they looked at, 6.4% average increase in predictive accuracy versus unimodal. Now keep in mind, MRI and PET scan isn't multimodal by their definition. So it's across disciplines of health. And like I said before, it has issues with scalability and time. And then the future, clear clinical deployment strategies, FDA approval and analysis of how using multimodal improves biases. So that's another key thing with that too. And then, so this is basically another representation of neurology. So it's in red. So typically Alzheimer's disease and mild cognitive impairment is the biggest factor for that. So you can see their study that I believe is 120 some papers over the past 10 years, just how things have been separated and how much more, the diseases such as Alzheimer's with a multimodal approach have been looked at. Now, out of these studies, it said 28 medical imaging and EHR. So this is a bimodal. So you have medical imaging, and then you have EHR. Then they said 10 fusion papers with imaging and genomics total. And you'll start to see, a bunch of these other papers here. So basically, uh, aggregation of MRIs, CSF, and genetics into advanced. So number three in specific was something that was, that the authors thought very high of because it's very hard to do. Anytime you do something that is really hard to do and that has scientific significance, like to benefit patients, is typically, you'll hear about a little bit more. And you'll see number four, late fusion, interpretable Alzheimer's diagnosis. So what that means is a lot of these machine learning and deep learning algorithms, they're not quite transparent. So I've got a paper kind of in my queue that basically says explainable AI, that you have these complex, potentially very helpful algorithms and basically understanding them better. So this paper, so artificial intelligence-based methods for fusion of electronic health records and imaging data. So this was a couple months ago this year, and the way I line these up is basically in this paper, it's just medical imaging and electronic health records. So that's experienced 2 times growth from 2020 through 2021. And in specific, 34 artificial intelligence studies. So early fusion accounting for 22, these disease prediction diagnoses accounting for most of them, 30, neurological disorders such as MCI and Alzheimer's disease, mild cognitive impairment and Alzheimer's, 16. And then so you have, machine learning, 19, DL, deep learning, 16, 13 use MRI, 8 use PET scans, mostly for AD, Alzheimer's disease prediction and diagnosis. So the whole purpose with this is the need clinical and laboratory data during image interpretation for radiologists, and in specific, high dimensionality, various statistical properties, and different missing patterns. So it says, I've mentioned this before, but 2 different types of imaging doesn't count as multimodal with MRI and PET. And it's looking at things as far as 5 different perspective analysis. You have fusion strategies, diseases, clinical outcomes with ML, data source types, and evaluation mechanism. So here's the breakdown with these is neurological disorders, out of 34 total account for 18 of the studies that they looked at. Alzheimer's 7, mild cognitive impairment 4, and you can see another one with stroke with 2, and then the dispersions between cancer, cardiovascular, and so on. So basically in all these things is that it's an iterative process. You'll keep seeing these papers, that pop up here. So multimodal growth is limited by absence of adequate data for benchmarking, and it lacks complexity in the used non-imaging data as well. Now, databases, ADNI or Alzheimer's disease neuroimaging initiative is commonly the most used as far as brain images. So these are PET scans or MRIs, and then these are followed by NAC, NCI, ADNI, TADPOL, and then MR clean, like magnetic resonance, like clean images. So as you see in this flywheel, basically, is if you start in the middle, you can see joint, late, and then early fusion. Now then, early fusion splits off between diagnosis and prediction. And then prediction, you could see, so the kind of this middle tier is neurological disorders. Alzheimer's disease is the primary component. And likewise for diagnosis, MCI or mild cognitive impairment and Alzheimer's disease are the principal components there of the papers looked at. So basically in all these things, this is a paper, it's Boston University, Tulane in Nebraska, and it's looking at clinical information, demographics, medical history, basically an assessment, another one of these kind of diagnosis papers. And what they found was basically their approach was favorable to neuroradiologists who, if they did it on their own, getting similar results. And that's not necessarily a bad thing because, they tend to be overworked. And I've heard reports as far as, having dozens of neuroradiologists in the same room trying to figure things out, basically. So they chose two models. So the first model is artificial intelligence, or ML, but it's MRI only. So that convolutional neural network, and they say that it surpasses the average diagnostic accuracy of practicing neuroradiologists. So then you have the fusion model, so that links CNN to a final non-imaging cat boost. So their cat boost is what they say what helps. So if it's not imaging, it's likely going to be like electronic health records. So they said in one of these, the performance of non-imaging model alone approached that of the fusion level. So a lot of these tests that they do to, potential seniors that have mild cognitive impairment or Alzheimer's disease is they're standardized quite well, and there's a battery of tests that they go through. So here's some of so it says brain regions that are most associated with the outcomes. So as you can see in A, with the MRI and dementia, and they're using this SHAP and demo score, what's showing up where, with if it's axial or, the different types of cuts, of images that we're seeing right here. So this next one is one to keep an eye on, because it's basically, so this is Berkeley paper, Cambridge, Lawrence Berkeley National Lab. And then this was April 2022. And they seem to have perhaps the best understanding and also the best vocabulary out of these papers as well. And basically what it is it's multimodal. So you have for beta amyloid, medial temporal lobe atrophy, tau, ApoE, and at MCI, mild cognitive impairment, and AD. So ApoE is typically a genetic marker that, if somebody has that, that's a stronger indication that they either, that they may get Alzheimer's. And this is for finer scale stratification and prognostication or prediction. So here's some of the things that they did. So the things that stick out for me is obviously you have trajectory molding at the top, and they use different types of this, neuroimaging database. So say if you have your ADNI, and then your the people there, and then the next step, sensitivity to future tau, is using ADNI3 or different database. And I believe that is either amyloid PET, potentially for ADNI2, and then amyloid tau for ADNI3. So it's just, basically what you're looking at, tau plaques or amyloid beta, tangles. And then, so basically they said this is their workflow. This is how they, went from, and I'll show you in some of these other ones. So these images, basically red is bad. So this top two images here, rate of future tau accumulation, is where it shows red, and those particular parts of the brain is that for these clinically declining people, is that, that's what's likely going to happen, say, in a prediction model. And then the clinically stable, you can see the rate of future tau accumulation, these two images at the bottom, that you don't see the red right there too. And here's another kind of close-up. So this is predicted versus observed tau accumulation. And then so observed, I believe, is on the left. And so you see prediction on your right. Basically, they provided a lot of diagrams and a lot of explanation as far as this might be something that would work for clinical use. So cognitively normal and MCI samples significantly accumulate tau in certain cases. And here's the algorithm behind it all. And this is what I'll be talking about on the quantum side, is basically support vector machine corroborates binary classification. And then their algorithm that they implemented was called a GMLVQ. So they said fewer patients are required in their studies because it's doing certain things. And, future rate of tau accumulation as a clinical outcome measure compared to future rate of cognitive decline, 31% reduction in sample size. Now, they keep posting these things, so you have to be careful in this specific paper, this Berkeley paper. But on average, 44% reduction in sample size, which is good. It's favorable. And then you see, tau accumulation explains up to 41% of the variance. So this is the type of paper, it's very technical, and they seem to kind of back up what they had to say. So multimodal stratification has greater statistical power to detect a clinically meaningful change in tau versus cognitive. So in this part here, so approach has potential relevance for the design of clinical trials. So this is kind of what I hinted at. And they say their multimodal method is more sensitive in capturing early stage AD related pathology than classification. So classification is typically binary, tertiary. But as you can see, one of the authors in these papers, they said there's a myriad of opportunities to do multimodal work beyond just like your standard EHR data alone, or you have your imaging data, just like a binary or tertiary, is that, incorporating these, especially, imaging and EHR, it seems to be having a pretty good effect. So, and they're, kind of forecasting that this could be for FDA, and basically their machine learning approach capitalizes on longitudinal data. So this next paper, so predicting conversion to Alzheimer's disease in individuals with mild cognitive impairment using clinically transferable features, is longitudinal data from ADNI databases. So ADNI, again, as I said, it has, MRIs, PET scans. I believe it also has a bunch of the extra kind of like hospital data that goes with it, because in these papers, it seems like they're working off that as well. So you have their two independent classification methods that they use, and it's for cognitive function, hippocampal volume, and here's the ApoE again. So this again is a genetic marker for Alzheimer's disease. So the two main ones is ensemble base, which is actually 5 different models, and they got 73% specificity, 63% sensitivity, and then you have random forest, which is a more common, not 5 different models, 70% specificity and 61% sensitivity roughly. And then this mesoscopic architecture paper is kind of interesting. So this is Imperial College London. So this is a predictive model using the mesoscopic architecture of the living brain to detect Alzheimer's disease. In other words, Alzheimer's disease diagnosis. So they used T1 weighted MRI scans with or without cognitive scores, and then this APV, Alzheimer's predictive vector. So this is kind of incorporating with the algorithm side of it. And then, so there's some examples of these things. So basically, single hidden layer neural network and predator-prey particle swarm optimization algorithm. And then you also have Sorensen et al. Linear discriminant analysis extracted cortical thickness. There's been 63%, and the previous author was 93%. So it really depends on what your is it area on the curve? Is it accuracy? These types of things. So, for instance, Tong et al. 0.78 area under the curve between healthy control and those with AD. And in all these, the devil's in the details. If you go through the methods, which specific data sets were they using, say, for instance, from ADNI or one of the other, databases as well. And then here's another one, 93, 90, 80%. 79% accuracy. So this is basically healthy control versus AD is relatively easy. So that's your 93%. And then kind of winding up, that 79% between stable and progressive. So if you have mild cognitive impairment, if you're stable, you're less likely to form Alzheimer's disease symptoms. If you're progressive, you're more likely to. So your accuracy kind of goes down between those two. So the overview of all this is basically their lasso approach. So you have your data set. So the top 3 are basically imaging, so ADNI, OASIS, IMC, and then cognitive scores. So this again is multimodal. So the MMSE is what I was referring to earlier. Is this is a score that's done to somebody that's suspected to either be, mild cognitively impaired or somebody that may have Alzheimer's, but it's found to be a very effective tool in combination with imaging. And this particular paper is cerebral spinal fluid biomarkers. So the ApoE4, I believe, is a blood test. But basically, these are the three different ones that they used for the paper. Now, in any of these things, they did image segmentation, features extraction, standardization, features reduction. You're pre-processing to the model. So your model has Lasso 1 and 2, Alzheimer's disease, MCI, and then in specific, 98% correctly classified in the non-Alzheimer's disease group, and then 76% for MCI and 92% for AD. Now, these two that they measure, so the APV1 did better. So they said state-of-the-art accuracy of 98%, and then they said 0.26 and 0.62 for the volume of the hippocampus and CSF, amyloid beta. And then APV2, a little bit less. I'll have a little diagram on APV2 and kind of like field strength for MRI. But basically, in all these things, the reason why these papers are so long is because it's crucial that they include all of this effort. And limitation, I'll touch on this as well, computational effort to pre-process. So this is typically, I think for most of these is GPU, but I'll kind of incorporate that as far as where things are going with quantum as well. And then the future studies, trying to get this to work on higher fields. So this is 3 Tesla is a higher field than 1.5. And the 3 Tesla, as you can see here, where it says unseen 3 Tesla ADNI data set, it was significantly lower in performance. There are other papers that I believe get their algorithms to work on 1.5 Tesla and 3 Tesla, which is kind of like the standard in hospitals. But as you can see that in this table set, just looking at the first row and going down, lower for bigger MRI magnets. Now, where all this ties in is basically, to get a better approach or understanding of quantum with all this is when you have programs and full stacks, is certain parts of it are very likely going to be quantum moving forward. So, with dynamic circuits getting better and National Science Foundation saying next year, 2023, we will have a practical quantum computer, is that you have to take these serious because there's certain things. So in this case, for classical layer was ResNet 34, and then, feature vector to this quantum circuit, quantum variational circuit that runs in a quantum device. And then it goes back to an operation that runs off of a conventional or classical hardware. And then, after that, you get your demented or non-demented. So this paper is kind of ahead of its time a little bit. There's been a number of other quantum machine learning for COVID. So COVID's a little bit easier. The CT scans, they're faster, and at that time it was more COVID, well, that pandemic times. But I would expect to see more of these. So this is essentially a binary classification using quantum machine learning hybrid, right? Because some parts of the code is being run on a conventional computer, some parts is being run on a quantum. Now, this is the proposed technology for chemical Q devices. Basically, this was adapted by Subaya et al. And so this top portion here is you need to train classically. So for instance, you have ADNI, MRI, PET, and this goes into ResNet 34. And then you have your generic tests. And then your specific data sets would be what you're testing for. So say, for instance, a patient MRI PET scan. And, going from here, this paper was classification. But like I said before, there's many current, so figure for many current machine learning, Alzheimer's disease, there's not only a lot of diagnosis, but there's a fair number of prediction too. So, I would expect to see a similar kind of path for quantum going into a lot of these things as well. And you can see that you can run either on a real quantum computer, which hopefully in 2023 we'll be able to a lot more. And then even as quantum computer simulators, some favorable results there with Penny Lane. with QML. So one of the things I want to take a look at is runtime. So for one of these papers, it's the Boston, Tulane, Nebraska paper. They used a really good i9 14 core, 3 gigahertz processor, these 4 NVIDIA RTX 2080 GPUs, Python, PyTorch, TensorFlow. And keep in mind, a lot of these things for quantum are somewhat similar. I know, especially between those three. And per GPU, the issue is getting 10 hours, to do a specific training. So if you could do, 4 of those at the same time, you have 4 done in 10 hours. So it'll be interesting because NVIDIA, they have a couple things. So it's Q Quantum, CU, and then Quantum. And then you also have CODA, QODA. You'll hear about Q Quantum, I think, a little bit more. So these are just specifics, and I think they depend. So typically in simulators, you could never go above, I think, 30. So it was interesting. I just read this. It said 10,000. So if you have 10,000 qubits, simulating in a relatively noiseless environment, that you can kind of see like the hybrid approach of doing quantum mechanics math on classical computers and it working, considerably better than it does today. And then they also said 287 times improvement in end-to-end VQE. I think this was for 20 qubits. And then say, for instance, 900 times speed up on quantum machine learning workloads. So it'd be interesting as you draw an arrow, going to the right, how will that 10 hours for these same tasks, be decreased with these? Now you have CPU and GPU, but now you have a QPU. Now, a little bit about the imaging market is so healthcare data is 30% of the world's data volume, and it has a 36% compounding annual growth rate. Now, imaging data accounts for 90% of that healthcare data, and over 5 billion global imaging procedures are performed per year. And then also global imaging AI medical market, compound annual growth rate of 45% with neurology. And we're kind of seeing that in the papers, but this is an industry, neurology such as, MCI, AD, or even stroke is accounting for the dominating share of the global AI imaging market. And then in specific, this has implications. So, for QML, so if you go up and down, like there was a paper, MIT, they had this huge symposium, and that it's just machine learning that they're using in all different places, segmentation, reconstruction. I know there's at least, is a MIT Seth Lloyd, there's at least one reconstruction paper, and that was, for medical image processing. So, you're going to start to see, it's just in this case, it makes sense to, run more on classical and at this part of the deck. It makes sense to run more on a quantum computer or simulator. And then this is basically stage one. So I presented on this last week, and it's basically this is unimodal in the sense of staying within imaging. But basically, the performance benefits with quantum are potentially better accuracy, lower cost to run. There was a paper I kind of focused on last week, is as quantum keeps going, is that, for certain cases that you can't run conventionally or, run much faster on quantum, since the computer's not going all that time that the classical computer would, you're going to likely see that benefit. And basically, the delighter with this is things will continue to improve, and there's already a number of developments in circuit optimization, meaning shrinking down your program. There's also developments, and there's also, these things are happening, is you can cut your pieces into, they're called dynamic circuits, so they can run on smaller quantum computers. And basically, the multimodal collaboration options for chemical Q device is this, to focus on, continue focusing on neuroimaging with these brain databases, so ADNI, MRI, PET, in specific MCI, AD prediction, Alzheimer's disease prediction. And now the variable, say in these three of them, because the omics and EHR have been going for a while, is going to be the quantum machine learning algorithm and optimizing that. And that's kind of like the new thing. People always want to do new things. Oh, we'll run this part on a quantum computer type of things. And then in omics, we talked about this before as far as, if it's a blood test, this is more fixed. And kind of, that's the approach is you don't want to change too many variables in order to prove that a new, piece of the multimodal framework here, that part is working, is to keep that fixed and likely as well. So EHRs, clinical data, use the current best ML algorithm. And again, the only thing that changes is the new quantum algorithm with the brain images. In specific, stage 2 is getting better neuroimages. So this is talking about better quantum sensing, and then all along medical imaging processing, evaluating which parts, say for reconstruction and image formation or enhancement, visualization, segmentation, which of those is kind of like, is taking significant amounts of time, potentially, as we saw, is the 10 hours with the GPU with this week's experiments. And basically, that's it. So stage 1 is developments with existing image databases, and quantum machine learning will present opportunities for Alzheimer's disease prediction improvements near term. And then image processing steps with emerging quantum technologies can likely be utilized to create better brain images. And then C is basically combining stage 1 and stage 2 with the better prediction and the better images to get an even better, a commensurate product, or one that is synergistic. And then stage D would be for the FDA submissions. And the chemical Q device mission statement is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and or resolution, combined with advanced prediction in neuroradiology for Alzheimer's disease. This includes quantum sensing, algorithms computing for MRI, PET, and QML neuroimaging techniques. And then some supplementary here too is basically the big names, the driving forces between quantum and healthcare. IBM Cleveland Clinic already working on finishing up. They said early 2023 of this quantum computer at Cleveland Clinic, NYU Langone, and Fermilab building a brand new quantum computer and quantum sensors to get better MRI analysis. National Institute for Quantum Science and Technology, I know they're working on quantum sensors for better MRI sensitivity. You have Mount Sinai Hospital Sandbox AQ for cybersecurity, patient security with quantum, and then the NSF, of course, the projected 2023 practical quantum computer. So the impact of all this is with QML. So QML, quantum machine learning, is the primary application in quantum computing. So researchers from Amgen, IBM, publishing IEEE, Roche QCware, and other papers such as NIH, BMC, which is Springer Nature. This is not a new thing. So quantum machine learning in healthcare, a lot of this has been going on, I think, for at least a year and a half, kind of like the bigger papers. And then, kind of everybody alluding to, when the computer gets awesome, the results will be reflected. So there is a fair number of competition that will likely adopt some form of quantum technologies, potentially even in 2023. Rigetti Stringworks was the last announcement, kind of in the quantum field, but they're saying quantum medical imaging, similar to chemical Q device. And then these others are more, AI, ML, DL. And then, like I said, with any of this, it's, potentially working with AWS or whoever, that they'll likely also get their quantum versions out where it makes sense. And then in healthcare, most of these companies are drug discovery. Okay, so there's approximations you have to make, but I've talked to at least one of these CEOs. They've said that it's something that the consumer would find need even with today's quantum annealing, which is a type of hardware, or simulators. So figure, not the full out simulation that we might see, further down the road, but there's progress getting made. And then especially keeping an eye on regulations, so CFR, ISO, IEC, NEMA, ASTM, and ANSI, is these will likely be required. IEEE Quantum has 9 of them out. But say, for instance, for FDA submission on this top row here, they're likely going to, say you need to meet this quantum algorithm requirement or quantum hardware development. And then here you go here. These are 10 of the last 2022 FDA AI ML software's medical device approvals. So the moral of the story is algorithms, or especially ones that are based on pre-existing images, tend to have the least number of regulatories listed on the approvals. And then those that are like full out systems, like a portable MRI, or say, for instance, GE's ultrasound, cardiac ultrasound, tended to have more requirements listed. And this is basically what's going on in a lot of people's brains. The biggest thing being focused on is the tau, because we hear of amyloid beta, and we've had amyloid beta PET scans, and now it's tau PET scans, and this is in some of these papers that's been reviewed today. And here's some of the Alzheimer's disease organizations to support, and then I'll have the references up, and let's see here. So I should be able to. Okay. Okay, so you should be able to come on if you have any questions. Be interested if you come from quantum or medical or both.
Okay, could you go back to slide 54?
Okay. Okay, go ahead.
Oh, I'm sorry, I'm not 50. Okay, well, 54 is fine. Okay, so I know that you know, quantum machines that they help with the search process, the search, when you have to search unsorted data, it's much quicker with a quantum computer. But then but what other parts of like machine learning would the quantum help with?
Yeah, so it's definitely training. So in at least one of these papers, it says that it's taking forever to train. And I think it is that GPU example. Basically, it's taking 10 hours on a single GPU to do our specific multimodal, task. And then they had 4 of them and split them apart. So that's always, imaging, and, the whole thing with auto sensing, Tesla's, that's always been a thing that people have thought is basically quantum would excel at. Now, I didn't put it in this deck. So, even if you start at image formation, you have detection. So that could be a new quantum or these diamond quantum sensors. There was just a breakthrough with a silicon vacancy, like two seconds of memory, basically. And then if you go down, so you have reconstruction algorithms. And I know MIT, I think it was 2020, they posted a medical imaging reconstruction. So that's basically, dealing with the raw data that you get from detection. And then you'll hear it, further down in image computing. The main thing is basically, the slide that I shared about the NVIDIA is there's certain things. Say, for instance, a GPU we know does better than a CPU typically, and there's certain things that we know a QPU would do better than a GPU. And this was kind of like an early example, even last year, as far as like your CPU is the brain, the GPU does a certain thing in graphics, and the QPU likely does something better. And this is based on qubits and low noise and all that kind of stuff. But I would say, after doing all this research, is basically, you know, you have to look at the specific algorithms, and then, you know, number one, what can you do today with a, say, for instance, like a penny lane simulator, and then in the other things is basically what can you, you know, what can you do with real hardware, those types of things. But yeah, there's, say, for instance, like, quantum computers simulating science. We know we can do that well. It's just caffeine is like, I think, 162 qubits. That's relatively low noise. So doing that inside of an environment like pharmaceuticals, making your own drugs efficiently, with the hardware right now, probably can't do that like as of December 2022. But yeah, that's what I found is basic. You have financial and transportation were kind of these first two. If you look some of the first papers, kind of getting big, 2019-ish, like quantum supremacy, you'll find a decent amount of financial papers. And of course, they're not awesome because the hardware wasn't awesome back then. But you'll see transportation. There's a fair number of transportation as well. But I just feel, I mean, if 2023 and quantum helps things, as far as whatever's going on, that there's so much work that's been done in quantum algorithms, and circuit optimization and figuring out dynamic circuits to cut them into pieces to run on smaller quantum computers, that a lot of things pretty well can happen, right? Because even if you look at Google's quantum supremacy back in October 2019, that one was, lots of error, but Google went back. They have a paper in Science, I think it's June of this year, using that same exact processor. And with quantum machine learning, so meaning with quantum sensing and specifically quantum memory, that all of that error is not quite as big anymore. So it's mitigated because you can hold on to something even if the quantum memory is only like microseconds back then, and now it's in seconds. Is that now there's all these workarounds that we're coming up with to kind of like do things really quickly because there's lots of noise. So that was an interesting paper too. But there's just, and the $20 billion in IBM, not just for quantum, but other things too. And President Biden visiting Arvind at IBM headquarters. And by the way, they just announced White House, like I think 10 new people in quantum, and that this mostly is cybersecurity. And there's a law now for federal agencies to incorporate quantum algorithms or PQC algorithms into conventional hardware.
All right, sounds good. Okay, and then could you go back to slide 48?
Okay, so tell me what it is, and then I'll see if it matches here. So the available QML tech, it's the staff notation.
I was looking at the circuit diagram.
Yeah, that's the one.
Okay.
Yeah, so I've spent a lot of time focusing on this paper. So this is basically MCI or AD does the patient have using QML in certain parts. And they said they got 97% compared to 92% using their quantum hybrid versus their classical approach.
Okay, and what is the significance of using all those RYs?
So I think those are rotational. So there's Hadamard,
rotational.
Yeah, rotational. There's courses that you could take with this. I've run a quantum circuit on IBM. It was like the recommended one, and then it shows you how long it takes, and basically I think it was like a 7-qubit simulator. So on this one, it's 4 qubits. So Q0 to Q3, and then you measure conventionally. So, and I think in most, if not all of these things, you always need classical computers. I don't think there's been a case where, as far as a functional or highly functional quantum computer. to do these. But these, I think these blue things are called swap gates. So a lot of times that in order to accommodate for noise, you have to do these changes to the circuits,
Mhm.
and just because the quantum computers are noisy, so
Okay.
they tend to escape. Like I said, we've gotten so good at programming and all these things that in anticipation of a better quantum computer.
Okay. Okay. So you're saying that they rotate just to help reduce the noise?
Yeah, so it just depends. So you would probably have to read up on it, but there, say for instance in classical, there's certain number of certain kinds of gates. To say if you have like and or but, well,
Yes.
quantum has their own gates, so they're not necessarily the same.
Mhm.
And one of the members that comes on, he says that a quantum gate isn't really physical. So it's
Yes.
just it's in that regards, it's different than classical.
Okay. Okay. And then what function do these like swap gates have, or did you know their function for this particular setup?
Yeah, like I said, I know they're used for it's to account for the noisiness of hardware. So the thing that's going on right now in quantum programming and circuit is circuit cutting, or it's dynamic circuits is what IBM calls it. So I believe this is I don't think this is simulator. I'd have to check. No, I think this is simulator. But basically, if you go to run on real hardware, there's things that work against your favor as you get higher in qubits, with noise as well. Like it kind of like it expounds on itself. So yeah, I watched a presentation. I can't remember I think it was a big company in US, and she was going through all these elaborate things of how she designed her quantum circuits, and it's to account for noise. And I asked her, I was like, well, what can we take that we have now and apply it so when the quantum computers get better? And she said it's completely different. Like these things that we're doing just to get it to run on quantum computers you know, is not even uh, it's not going to be around likely as, qubits increase and noise decreases. So,
Oh, okay. Yeah, and yeah, I'm thinking that there would be more to this circuit diagram, more of these quantum gates for like something that they really have, because all I'm seeing is, you start at well, you do the Hadamard gate, which creates it in a superposition, and then you rotate it, to deal with the noise. And then you got these swap, which you're saying are likely due to the noise, and then you got the measurement. So it doesn't really look like it's doing anything other than accounting for noise. So I guess this is perhaps a simplified version, or maybe just something that sort of illustrates, how you deal with the noise, because I don't really see anything here that really does the logic for for anything.
yeah, it's because so you're talking about entanglement here too.
Yes.
So that's why I say, like, if you really want to understand this stuff, because there's other times, say if this is Penny Lane, this quantum simulator, that you know the circuits you usually run on a simulator to make sure it runs, and then you try to run it on, say, the next IBM, but it's just so noisy that the results aren't as good. So for instance, if this is Penny Lane, then it tends to be slower. It's not a classical computer, but then there's certain things that are slow on quantum too. But there's whole different trainings on a lot of these different things. And There's a University of Toronto. There's I think it's a 9 or 10 week QML, so quantum machine learning. Uh, and then you learn all about that stuff. I think it's free. You could just audit it. So I don't think you have to take the courses, but I think it's pretty rigorous because a lot of courses are, 3, 4 weeks.
Okay.
And
And what was that? University of Toronto?
yeah, it's on edX, so edx.org. But yeah, I think it's just called QML or quantum machine learning, something like how to program or fundamentals or something like that. And I know there's a ton of Qiskit resources. It's all open source. And I've gleaned off of YouTube, they'll do a specific. So, how I was talking about when they ran on the simulator, they got close to say they expected 50-50 results. And then on the noisy quantum computer, it might have been 6, 12 months ago, is that it was doing its thing, but the noise was messing up the distribution. So it didn't quite get to 50-50. So, that's where all this creativity comes in, with making circuits that will run okay on real hardware. But I don't know if they've released Osprey in Qiskit yet, because when I went to program, I only saw the Eagle, which is 127, and I had like a Bell State analyzer, a smaller one, and I just run, like I said, like on a 7 qubit simulator. But there there are a decent number of things in the pipeline right now. So that the reason why I keep saying dynamic circuit cutting, there was an HPC wire paper that basically said that now that you have this, IBM's it looks like IBM may shift their map more towards commercialization today, chopping up, say, like a 100 qubit circuit into 6 and 7 qubit pieces and running them, and opposed to a million qubits. The quest for error-free million qubits is that the way things are looking right now is that it's kind of a big deal, that we can segment into fragments and actually run it on real smaller quantum computers. And it's sounding like I've seen companies or startups take their whole team on a flight up to IBM. And with the 433 qubits, they say because of dynamic circuits, as you can run late next year in 2023, 16,000 qubits. So, but I'm sure there's certain cases where you're losing something. I think you lose either, say, CPU power or something because you're running into a bunch of different, there is a trade-off into running these smaller chopped up programs.
Okay, yeah, because yeah, I've actually been studying quantum computing a lot. Looked at articles and looked at books, and I see these circuit diagrams for the quantum computer, and it seems like they don't really explain what what specifically is doing. What is the what is physically, why, I mean, why do we have a rotation? How does that help
Yeah.
the algorithm?
Yeah, I mean, if you want to do, because I'll probably focus on QML with penny lane, just because I think that's primarily the thing that they focus on. And I've come across, like I think at least 4 or 5 papers that use penny lane for QML. Now, as far as the whole thing, and I think ion trap and gate-based superconducting, so like IBM and IonQ, are compatible. Like they're gate-based. You don't need special programs. That you can run certain things on superconducting qubits, other things on ion trap. And then I do know for IBM, there's a little notepad. So then you can copy and paste their code into yours. And then as you start to grow with it, then you have that in your pad, like they want you to. There's a website called Papers with Code, and then so I found a more advanced QML paper, and then you can copy, basically you're learning off that code. So that's just how it is. Somebody will find out something, and then
Okay.
it's kind of open source. So
Okay. Okay. Yeah. Yeah. I'm still working on. So yeah. I'm thinking I'm understanding it better now. The circuit that you showed. So we get like, you know, all of them are rotated about the y-axis, and then the swap it entangles them, and that's one of the main ideas behind entanglement. So the main idea behind quantum computing is you have a bunch of different states, like more than I could say, like trillions and trillions, or even higher than that, different states that are kind of like, I don't know, doing their thing. And then because they're entangled, their wave functions interfere with each other, and so they cancel out. So you have constructive interference, you have destructive interference, which cancels most of them out. Then you have constructive interference, which which shows what are the ones that are likely to be the right answer. So like this qubit coupled with this qubit, that's likely to give the right answer. So this variational algorithm, it may be complete. I mean this variational algorithm that's shown by the circuit, it may be complete as it is. I'm just not really. I just need to kind of understand that the steps better. Why, how does that
yeah,
actually
I mean,
work?
I've looked at programming courses, and they expect you to have your own software, and then you're online, and there's
Uh,
like 5 or 10 other people, and then they tell you what to do, and then you do it on your own software, and then you report back. I didn't have the software, so it wasn't a it was a learning experience for sure, but the other students or attendees would report that this it either ran or it didn't, you know. So, but yeah, I couldn't tell you like how many different resources I come across, and here's so Xgate, Polygate, and then they say think of the classical's NOT gate, so it's similar to the NOT gate. Now, a lot of people talk about this. The block sphere is the geometric image of the states of qubits.
mhm.
Um, but we are at the subatomic level. It may be easier to think of the states of qubits as snapshots of an electron zipping around an atom. So they go hand in hand, because if you understand like your physics, you understand the physics of particles, and probably subatomic particles.
Right.
Um, but I think everything is on the web. It just takes the will and the desire, and you got to get hooked on it, right? Because I get caught up with other things, because for the startup, but many programmers, that's what they do, is they code all night, and maybe different work schedules, that kind of stuff, because they're
Mhm.
trying to get it to run. And then in San Diego here, we have tech coffees, and then those have a bunch of programmers that show up. So I'm starting to cross into that space, a little bit more. But I have to keep an eye on everything as far as medical too. So yeah, just find a group of